So let's get started with some questions here. The first question for you is, a positively charged proton is first placed at rest at position 1 and then later at position 2. So here is position 1, here is position 2 in a region where electrical potential is described like this. So here this is a equipotential line with 0 voltage, this is with 1 volt, this is 2 volt, 3 volt, 4 volt. The question that you are being asked is, which set of arrows on the left below best describes the relative magnitudes and direction of the electric force exerted on the proton when it is placed at position 1 and at position 2. Okay, so does everybody understand the question? This time your test charge is a proton and you put it at position 1, you put it at position 2, and the question is asking you to find the relative magnitude and direction of the electric force that the proton will feel when it's placed at position 1 and position 2. Everybody should be talking to a person next to them. You have 1 minute to answer this question. All right, 5 seconds, folks. All right, it turns out that the correct answer here is D. Okay, why is D the correct answer? First of all, everybody should be able to see here that the higher potential is on this side, so that means which side is more, you know, like, I mean, if suppose you're thinking in your mind that there might be some positive charges somewhere and there's some negative charges somewhere else, remember this is a case where the electric field is constant. That is not a case where the electric field is constant. Do you see the electric field is varying? How can you say that the electric field is varying? Anybody? Go ahead, please.
Because the lines get closer and closer together.
Very good, because if you see, oh, here delta V is the same, it's 5 volt going to 4 volt, but the lines are farther apart, these equipotential surfaces, right? On the other hand, here this is 1 volt and this is 0 volt, so delta V is here again 1 volt, but these lines are closer together, and that means the electric field in this region is stronger than the electric field in this region. In fact, the electric field keeps getting stronger and stronger as you keep getting on this, going to this side, because of the fact that and you can see this from the equipotential lines getting closer and closer together, right? Do you remember this? Because remember last time we had learned this, that V final minus V initial should be equal to negative of integral E dot dl from the initial to final. Do you remember this? And from here, let's say that the electric field was at least constant between, say, 5 volt and 4 volt. Let's say that electric field is constant between this. Then in that case, you can pull the electric field out of this integral in that region only, not in the rest of the region, and you can say that this is E at dl, and obviously if, you know, you can choose your dl to be anything. If suppose you are trying to go from this surface to this surface, it's better for us to choose our dl's in this direction perpendicular to these surfaces, right? Because that would make our calculation easy, because that will make cosine theta here cosine 0, right, if the electric field and dl are in the same direction, and then we are just left with integral magnitude of dl from the initial to the final point. And you can see that this integral dl just turns out to be what? Integral dl is just the distance that you're moving. So if you're moving from here to here, then that's your dl, the distance between those two plates or those two surfaces, equipotential surfaces. There may not be any real surface there. There is definitely some electric field between those two equipotential surfaces, right? And so from here you can immediately see what I'm trying to show you is that the electric field is negative of Vf minus Vi divided by L. I don't care about the negative sign here. Let's not even worry about that. So we can just get rid of this. I'm just interested right now in magnitude, you know, this is the relation between magnitude. Is everybody appreciating, and we did this yesterday already. The point that I'm trying to make is the way to figure out what the electric field is not just to see what is the potential difference. You also have to see what is the distance between those equipotential surfaces. So if the distance is larger, if L is larger here compared to say L here, delta V is the same, 1 volt going to 0 volt, delta V is 1 volt, delta V is 1 volt here also. So the numerator is the same in both places, but the denominator is different. Do you see that? Is everybody seeing L is more here than here? And therefore, the electric field is stronger here than here. We also know that in these cases, we always know the potential is higher, closer to positive charges, right? So we know that somehow these places are at a higher potential, these are at a lower potential, and so the electric field must be pointing in this direction, right? And therefore, if you put a positive charge here at point 2 or point 1, which way will it feel a force? In the direction of electric field, because F is equal to QE, and since this charge is positive, it's a proton, that we know that this is going to be force and electric field are in the same direction. So we know the force will be in this direction, right, from the surface of higher equipotential to lower equipotential. So the correct answers can only be these two, one of these two. But since the electric field is stronger here than over there, by this reasoning, we know that the force is larger at this point because the field is stronger compared to the other point. Is everybody clear on this? Any questions about this? Okay, let's move on to the next question then. So the correct answer here was D. Let's move on to the next question. Okay, it says the equipotential surfaces associated with an isolated point charge are, and your choices are radially outward from the charge, vertical planes, concentric spheres centered at the charge, horizontal planes, concentric cylinders centered at the charge. You have 1 minute, you can talk to a person next to you. So why is the answer concentric spheres? It looks like most of you got it right, because if you remember, the electric field due to a point charge is radially outward from it if it's positive and radially towards it if it's negative. So these are the electric field lines, right? That's not equipotential surface. Equipotential surface is a surface where the potential is the same, and if you remember, the potential due to a point charge at a distance r away is V is equal to K Q divided by R if this charge is Q. So in other words, you can see that potential is a scalar quantity, so there's no direction, and so all the points that are at the same distance r away from this charge will have the same potential. And a sphere which is concentric with the point charge, with the point charge at the center, will be one equipotential surface. So maybe the potential here everywhere is say 10 volts. Maybe there's another equipotential surface over here where the potential is 8 volts. That's another equipotential surface. There could be another one here. You know, there are infinite number of concentric equipotential surfaces due to this point charge. Does that make sense? Any questions? Okay. So the correct answer here is C. Let's look at the next question. Okay, this one, let's wait till we have actually done the material. All right, so today we are going to talk about capacitors and capacitances. We have already mentioned this word capacitor many times. What do you think comes to your mind when you think of the word capacitor? That's true. I mean, the thing is, it turns out that capacitors are part of, you know, all of the electronic circuitry that you see, you know. So capacitors look like this, and if you look at any integrated circuit chip, those things. Capacitors are an integral part of that. You know, you will see a lot of resistors there, you will see a lot of inductors there, and you will see a lot of capacitors there in all of those integrated circuits. So the first element of those integrated circuits that we are trying to learn are capacitors, and they come in many varieties. You can see they look, you know, many of them look very different from other ones, but they must have something in common, and that's what I'm asking you. What is it in common that they all have? When will you call something a capacitor? And we have discussed this in the past, so you should be able to answer this question, because capacitors have kept coming up starting from the first chapter that we have learned. And now the next 2 chapters are totally dedicated to capacitors. But you have heard this word many times before in your textbook and in this lecture as well. Any thoughts on when would I call something a capacitor? Go ahead, please. Constant electric field is not a necessary thing for a capacitor. I mean, but there is some requirement for calling some kind of a configuration a capacitor. When would I call something a capacitor? Go ahead, please. Okay, when it stores charge. Okay, that it turns out capacitors will store charges and energy, electrical energy, but still, I mean, I want to know what kind of, you know, if you show me something, how do I know that this is what I should be calling a capacitor? Because many of them look very different from each other. Go ahead.
Would there have to be an electric potential on both sides of the capacitor?
Okay, there definitely, you know, will be an electric potential between, you know, plates of a capacitor if you put opposite charges on them. But when will I call a particular, you know, if you had to make a capacitor, how will you make it? Huh? So capacitor definitely has some conductors. So the thing is, what the answer that I want from you is capacitor will always have 2 conductors separated by an insulator. It could be vacuum also between the 2 things. So if you have any 2 conductors which is separated by an insulator in the middle, or insulator could be nothing, you know, vacuum also, so it doesn't have to be an insulator. It could be an insulator, wood or water or plastic or PVC, but the point is, if you have 2 conductors separated by an insulator or vacuum, that is what you call a capacitor. That is by definition, that setup is called a capacitor. So thanks, you. Okay, and the example that you have seen, the example of a capacitor that you've seen is this thing, which we call parallel plate capacitor, and this is what has come up over and over again. You know, you've done this in your exploration, you've seen this in chapter 21, chapter 22, every single chapter. You can see there's a conductor here, or metal here, there's a metal there, and in between the 2 there is air. You know, air is an insulator. So this configuration is called a capacitor. You could even have 2, one spherical conductor, and outside that you could have another spherical conductor which is concentric with it, and suppose, you know, the 2 things are not touching each other, but there's some kind of air in between them, or let's say some kind of an insulator, wood or something, that would also be called a capacitor. You could have 2 metal cylinders, and then there could be some insulator in between them, that's also a capacitor. All of these are different types of capacitors, and today we are actually going to talk about all those different kinds of capacitors. But before we talk about capacitors in general, let's get to some point that was brought up here, which is one important property of all of these capacitors is to store charge and energy. That's a very important usage of all these capacitors. You know, when you put, let's say, you know, you have this parallel plate capacitor, and suppose you put plus charge on one of the plates and negative charge on the other plate, what happens now? There is an electric field between the 2 plates, right? And because there is an electric field, there is some energy that is stored in electric field. And so capacitors can be used to store energy. And in fact, today we are also going to talk about how to find how much is the energy stored between the plates of a capacitor. In fact, this energy stored between the plates of a capacitor can be very useful in many applications. For example, pacemakers. You know, if somebody's heart is not working very well, they use pacemakers. Pacemakers make use of capacitors. Similarly, your windshield wipers, they make use of capacitors. It turns out this energy stored in the capacitor can be used to pass current. The difference between the current that this capacitor, the charges that are stored on the capacitor plate will pass is somewhat different from the current that will be due to a battery, because usually when you think of a 3-volt battery or 5-volt battery, those kinds of things in a given circuit will typically give out the same current unless there is a capacitor in that circuit. So somehow capacitor will give out current that may not be constant, that may be increasing and then decreasing, increasing and decreasing, or you can tailor it to your application based upon how the capacitor is connected with everything else. And we will talk about all of that. The rest of this course is really about talking a lot about these circuits and what are the usage of this capacitor. You will see this will not go away till maybe the next 5-6 chapters will keep discussing what the capacitors are about and why they are useful. But the point is capacitors can store energy. Now here is the thing. What would be one way of charging the capacitor? One way of charging the capacitor would be just to do it the way you did it in your exploration assignment. So look, right now there is no charge on any of these plates. This voltmeter is reading 0, right? But I can actually rub this thing, okay, so I generated some kind of charge on this. Let's say that was positive charge. Now if I put this metal thing which has a lower surface and an upper surface, if I ground it, do you see that there was charge separation on the metal plate? Do you see that that thing is moving? So basically what happened, I basically said, okay, so I rub this insulating surface, it developed some kind of charge, I put this metal thing on top of it, there were charges induced, negative and positive. When I grounded it, what happens? Which kind of charge will get neutralized? The one that's not very, that the system doesn't like. So negatives, these positive charges love, right? But these positives are being repelled. They might as well run away if they could. And now if you're connecting it to the earth is a huge conductor. So these positive charges now will get neutralized by electrons coming from the ground. So these things get neutralized. So now you only have negative. Now if you lift it, which is what I did, so you remove the grounding wire, then you lift it, and when you lift it, do you see this has negative charges? When I touch that thing to this, some of the negative charges went to that plate, right? Because that's a conductor, this is a conductor, wouldn't some charges move on to that? Now if some charges moved on to that, some negative charges move on to that, what do you think will happen to this plate? I just touched that. Do you think there will be induced charges on this? Yes. So there will be, what will happen is that, so this is the negative, this is one plate, this is the other plate. So if you put negative charges by touching this plate with this thing which was charged, this thing develops negative charge. Because of this induction now, this thing develops positive on one side and negative on the other side, right? And now if this thing is grounded, which it is, the thing that is not liked by the system will go to the ground. So for example, I'm saying this will develop positives on this surface, negatives on this surface, right? Now if I ground this system, do you see these negatives don't like being close to these negatives? So these negatives run away to the ground, and now what you have is negative charges next to positive, right? And you have an electric field between that. So now this thing has electrical energy stored between the two plates. But doing it with electrophorus is not what usually is done in electronic circuits. Do you think that's the way people charge capacitors in electronic circuits? No. In fact, in all electronics, in all of electronics, do you know that your computers and things, they always use this binary system of zeros and ones? Right? Everything, all the data is stored in terms of bits, which are zeros or ones. Now, what is a 0 and what is a 1 in a computer? It turns out that all of those zeros and ones, all of those registers actually have lots of capacitors. Each of them is a capacitor. And the point is that if the voltage on the if the potential difference, by the way, now we are going to start using a new term called voltage, and voltage word is exactly the same as potential difference. Okay? So these are synonymous words. So remember that whenever I use the word voltage, so when I say the voltage of this battery is 3 volts or 5 volts, or the voltage across the plates of a capacitor is 3 volts, you know, if I say this is plate A, this is plate B, and VAB is equal to 3 volts, all I'm saying is that the potential difference between these two plates is 3 volts. And I already know which plate is 3 volts higher than the other one. Which one is at a higher potential? The positive plate or the negative plate? The positive. The positive is always higher, right? So when I say this, the potential difference is 3 volts, I'm saying this is 3 volts higher than that one. If I choose to call this plate 0 potential, this will be 3. If you choose to call it, you know, 5 volts, then this is 8, etc. Okay, so voltage is equal to potential difference. This word you should know. But what I'm trying to say is that the way electronic circuits, all of the electronic circuits do this 0 1 stuff. You know, when do you decide something is 0? Some register has a 0 in it or a 1. They do, you know, these bits and bytes. What is a bit? A bit can be a 0 or a 1, right? 8 bits are a byte. The thing is, each of the bit is really a capacitor. And if the potential difference, it's already been decided ahead of time, if the potential difference across a capacitor is less than a certain voltage, we are going to call it a 0. That'll be a 0. If it's above a certain value, let's call it a 1. And so imagine in an electronic circuit you have lots and lots of teeny tiny capacitors. Not this huge, these are huge. I mean, those are so tiny that you really, you know, in a small chip you can fit a very large number of them. But the point is that when the voltage across those capacitors is less than a certain cutoff value, you call it as bit of 0, otherwise you call it a bit of 1. Okay? So capacitors are very pervasive. Now you can see that obviously you are not going to keep rubbing something and keep charging them. So what would be a good way of charging them and causing a potential difference greater than or smaller than a certain value? Maybe connecting them to a battery or something? Yes, and that would be a way of charging that we are going to use most of the time in this course. So what is a battery? Any thoughts on what a battery is? Everybody knows what a battery is. It turns out battery is something that has a potential. When you connect a battery in a circuit, the battery has a potential difference across it, and what it does is it causes a force on the electron, because remember, potential difference is related. Vf minus Vi is potential difference or voltage, right? And that is related to electric field. So when I say there is a potential difference between this point and this point, would you say that there is an electric field that is not 0? Wouldn't you? Yes. So potential difference is totally related to electric field. In fact, in the last class, I showed you using that relation how to find the electric field from potential difference, how to find potential difference from electric field for lots of different cases. That's what the last class was dedicated to. So you should keep this in mind, that these are two different languages for talking about the same thing. So anytime you say, oh, this battery has a potential difference of 3 volts, that means when you connect it to wires and complete a full circuit, there will be an electric field, and that electric field will cause a force on the free electron in the conductors, in the wire. F is equal to QE, right? So potential difference implies electric field implies a force on the free electrons that can start moving in a wire. And so in this course, the battery, and this is a standard notation in a circuit, will be denoted by this kind of a symbol, where I'll have one tall line and one short line. Tall line will mean the positive terminal of the battery, and short line will mean the negative terminal of the battery. So that means basically what you are saying, and battery will have some potential difference. You know, you will say VAB for the battery is, say, 3 volts. What does it mean? It means that this positive terminal is 3 volts higher than the negative. The mechanism by which a battery, you know, develops positive and negative, I mean, one of the electrodes becomes higher than the other one is different from this capacitor. Okay, here you have two, in a traditional battery you might have two electrodes dipped in some solution. When you connect it to a circuit, it turns out some chemical reactions will take place and they will produce this electrical, this difference in potential, and that will create a force, electric field, which will create a force on the electrons. Okay, now in a circuit, a capacitor, how would you represent a capacitor? A capacitor in a circuit would be represented with two lines, equal lines. This would be a symbol for capacitor, and that would be the symbol for a battery. Here, let me write. Okay, battery will start to, electrons will start to flow in a wire as soon as you connect a battery to it and complete a circuit. So for example, let's say that we had a capacitor. This is a capacitor, and here is a battery, plus and minus. So this is my battery with some VAB. Let's say it's a 3-volt battery, and these are all wires. By wire I mean these are conductors. Okay, do you see now the circuit is complete? Here is the thing, and this is some capacitor. I want to define something about capacitor. I want to teach you something about something called capacitance of a capacitor. How would you know how much charge this capacitor will develop on its plates? Okay, let's try to think about it. So what do you think will happen? Does anybody have a thought? So let's keep a switch first. Let's say we have a switch. Initially it was open. As soon as right now it's an open circuit. Okay, but the thing is, as soon as I close this switch, what do you think will happen? We are saying this side is 3 volts lower than this side. There is a potential difference. This potential difference will cause a force on the electrons, and you know what the electrons will do? They will start to accelerate, right? F is equal to QE, and the electrons will accelerate. They'll want to go from the negative towards the positive. Now what do you think will happen when the electrons come here? Any thoughts? Because I'm saying a capacitor will always have an insulator in the middle. It could be air, it could be nothing, vacuum, or it could be wood, or it could be plastic, but there's an insulator. Insulators don't have any free electrons. So what do you think will happen here? Go ahead, please.
They'll build up on one side.
So what is building up? So what do you think is building up here? Very good. Negative charges will stop here. These negative charges will stop here, and where were they coming from? If you think of it, the electrons do have a path to go this way. They only cannot go here because this is an insulator here, right? Or vacuum, nothing. So electrons really were coming from this, this side, and these positive charges are left behind because the electrons went and they accumulated there. Is this making sense? This is the process of charging a capacitor plate using a method different from what I showed you. This is using some battery. You're trying to charge a capacitor. Now do you think that this, electrons will keep accumulating forever? What do you think is happening as a function of time? Any thoughts, folks? Do the thinking, because these are, physics should be something that you should be able to think about it. It's not about me telling you what should happen. You should be able to think through these things. Go ahead, please.
Closer to the potential of the battery.
Very good. So the thing is, what you notice is that as more and more electrons go and get dumped on some plate, let's say this plate, won't those electrons repel more electrons that are trying to come and perch themselves there? Do you see what I'm saying? So in other words, what we are trying to say is that as more and more charges are building up here, there is an electric field that is building up here, right? And this electric field is actually trying to push the electrons back. It's saying, no, don't come. You know, so as these electrons hate more electrons from coming, they are pushing them back. So there are two things that are going on. This battery is trying to push the electrons this way. The charges that are accumulated here are trying to push it the other way. And what he correctly pointed out, when, see, as the electric field is building, would you say there is a potential difference building up? Yeah, electric field is related to potential difference. So you can see, in fact, here is the relation. Electric field in this case will be this. Electric field is related to potential difference like this. So we can see that when the voltage here between the two plates becomes the battery voltage 3 volts, at that point the force with which the battery is trying to send the electrons this way will be exactly the same as the force with which, you know, this electric field or this potential difference is trying to send back the electron. At that point, what happens? The electrons don't move anymore, you know, they'll stop accelerating, right? And at that point the current will stop. And then you say, okay, for this battery, that's the maximum amount of charge I can put on these plates. So this is plus Q, an equal amount of electrons have gotten accumulated here, that's minus Q. Is that making sense, folks? What I'm talking about? What do you think will happen if I change now if I change the battery voltage, make it 6 volts? Do you think that now this battery is more powerful, right? Will it again start, you know, will it again exert a greater force to send them this way than this 3 volt thing that's trying to stop the electrons from coming here? Yes. So in this case what you'll see is that electrons will again start to move, and they'll more and more charges will accumulate, and let's say the charge accumulating here is Q2, and that would be the case when the voltage has become 6 volt here, the same as the battery voltage, again the current will stop. These electrons are not accelerating anymore. Is that making sense? Similarly, if this was a 9 volt battery, would you expect more charges to accumulate here on the plates before the current stops? Yes. And so what you learn from here, what you have learned is this, that the charge that is accumulating on each plate of the capacitor, you know, I'm talking about the magnitude of charge that accumulates on each plate of the capacitor. Of course, if this is plus Q, then this is minus Q, right? I don't care about the sign right now, I'm just talking about the charge that is stored on each plate of a capacitor, magnitude. Do you see that this is proportional to the battery voltage? This symbol, is everybody familiar with this symbol, proportional to? What I'm trying to say is if this was 3 volt, there will be some charge. If this became 6 volt, this charge will be more, 9 volt, even more, etc. So higher is this battery voltage, higher is the charge accumulating, right? And you can turn this proportionality into an equality by saying that Q is equal to a proportionality constant times VAB. And this proportionality constant is what is called capacitance of a capacitor. Okay? Is everybody familiar with going from proportionality to an equality by putting a constant? So this constant is called C is equal to the constant of proportionality and this is called capacitance of a capacitor. Okay, look at that relation. You can see that I can define this constant C as Q divided by VAB. So one way to say what is the capacitance of a given capacitor, like for example this parallel plate capacitor, would be capacitance is defined as the charge stored per unit voltage, right? Do you see it's charge per unit potential difference or voltage? Remember, voltage and potential difference are the same things, right? Anybody wants to tell me what would be the SI unit of capacitance? Somebody from the third row, please. I don't want some fancy names. I want to look at that relation and come up with a unit for capacitance. Nothing fancy. I want, no cool names. It should be just something based upon what's written there. What should be the unit? Go ahead, please. Excellent. The unit of capacitance should be the unit of charge divided by unit of potential difference, and that should be Coulomb per volt, right? So SI unit of capacitance is Coulomb per volt, and Coulomb per volt does have a cool name after a scientist who did a lot of work related to this. It's called Farad. So, and you can denote it with a symbol F. So Farad is nothing but a nickname for Coulomb divided by volt. 1 Coulomb divided by 1 volt is called 1 Farad. Okay? Any questions about capacitance? Is everybody clear on capacitance? Now here is the thing. I think that this thing can be very difficult, because I know I've given questions in exams like that and people have not done very well, and that's why I keep pointing out these things. What you have to understand, if I ask you, the capacitance of a capacitor depends upon the charge on the plates or the potential difference of the battery that is charging the capacitor, what would you say? Would you say yes or no? It turns out the answer is no. And I'm telling you, either on the midterm or your final exam, you will have a question like this, because I always ask this kind of question, and this is a very hard question, because the thing is, do not just look at the formula as a memorization tool. You have to understand something. So the point is, the capacitance of a capacitor only depends upon the geometrical property of that capacitor. It depends upon, for example, what is the distance between the plates, how much is this cross-sectional area, pi r square, and it will depend upon, do you have water here or air here or vacuum here, etc. It will not depend upon Q or V. Why won't it? Go ahead. Were you going to say why it doesn't depend upon Q or V?
No, I was going to ask what the initial question you asked.
Oh, the question was, does the capacitance of a capacitor depend upon Q or V? That was the question. And the answer to that question is, no, it doesn't. And why doesn't it? In fact, I've already proved to you by doing this thing here. If you think about what I talked about here, you should already see that it doesn't depend upon Q and V. Why? Because if you increase V, what happens to Q? Q increases such that the ratio of the two stays constant. That's the constant, capacitance. Do you see? It's a proportionality constant. It's a constant. So what it says is that if you increase V, Q will increase such that the ratio of the two stays constant. Does that make sense? So C is actually a constant that only depends upon the geometrical property of the capacitor. How much is the area of cross section? How much is the distance between plates? That's it. It does not depend upon Q or V. Because increasing V will increase Q such that the ratio of the two will stay constant for a given capacitor, right? And so, since we are at this point, does this thing make sense to you? Let's prove it. Let's now try to figure out what would be the capacitance of a parallel plate capacitor. It's very easy to do. So let's try to figure out what is the capacitance of this parallel plate capacitor, and let's say that the distance between the two plates is D, and let's say that the area of cross section of each of these plates, pi r square in this case, or if you have a rectangular plate, then it will be, if you had two plates like this, then the area of cross section would be length times breadth, right? A. So I claim that the capacitance of a capacitor will only depend upon geometrical property. So let's try to figure out capacitance of a parallel plate capacitor. Okay, so parallel plate capacitor is this. You have a positive plate, sorry, you have one plate which you can charge with positive charge, the other plate is charged with negative charge, and now there is some electric field, there's some potential difference, VAB, if we decide to call this plate A and this plate B. Okay, let's say that the area of cross section of each plate is A. And let's say that the distance between the two plates is D, each plate. So D is this distance between the two plates. And right now, let's just keep air between the two, or vacuum. So that means let's say there's nothing between the two plates. Okay, so here is the thing. Do you remember from a while ago what was the electric field between the plates of a capacitor? First of all, if you just had one infinite sheet of charge, because we are assuming these plates are so huge that you can think of them as infinite sheets. Remember that? Anybody remembers? Go ahead, please. Very good. The electric field due to one sheet will be sigma over 2 epsilon 0, and if you put two sheets with opposite charges, you can see, you can think about it, the electric field due to the positive plate will be this way, and due to the negative plate will be towards it also, and each of them is sigma over 2 epsilon 0, and the other one sigma over 2 epsilon 0. You add them up, the electric field between the plates here has a magnitude of sigma over epsilon 0. Is that kind of ringing a bell, folks? We have already done it twice at least, in this course. Once in chapter 21 when we were talking about a disk of charge and we generalized it all the way. The second time when we were doing Gauss's law for an infinite sheet of charge. So this is the third time you are seeing that the electric field between the plates of a capacitor, E, has a magnitude of sigma divided by epsilon 0. Now what is sigma? If suppose the charge on this plate is Q and this one is minus Q, I'm worrying about, how much is the charge per unit area, right? What would it be? If area of the plate is A, Q is the charge, sigma would be? Somebody from the last row. Sigma is what? Charge per unit area. So what can I write sigma as? Can I write it as Q over A? Okay, good. Very good. Okay, so this is the electric field. Now what is the potential difference? Notice that for a parallel plate capacitor, the electric field between the two plates is constant, right? It's the same thing, sigma over epsilon 0 everywhere. I want to know what is VAB. So I really want to know VAB. Can I find VAB from the electric field? Yeah, if the electric field is constant, this is the relation between electric field and VAB. This is my VAB between the two plates, right? So the thing is, I know I can use this. If the electric field is constant, I can pull it out, which it is for parallel plate capacitor with infinite plate areas, which we are going to assume here always. And so I get this in the end. I don't care about the sign. So basically the magnitude of electric field is VAB divided by the distance between the plates, right? So what I find is that electric field can also be written as the potential difference between the two plates, VAB, divided by the distance between the two plates, D. Is everybody with me? Yeah? So this is just coming from the relation between electric field and potential difference. Any questions, folks? Okay, so we are set then. Using both of these relations, what do you find? Can I say that this then must be equal to this? Okay, so we are almost there. So then we can say, using those two, VAB divided by the distance between the plates is equal to Q divided by A times epsilon 0. Can you rearrange this equation? I want all of you to rearrange this equation and tell me what is the capacitance, because we already said capacitance is defined like this. Capacitance is defined as Q divided by VAB. So you tell me what is capacitance equal to. Just rearrange this and tell me what is the capacitance of this parallel plate capacitor in terms of its area of cross section and in terms of distance between the plates. 1 minute, talk to a person next to you. All right, somebody from the second row, please. Anybody from the second row? Go ahead, please. Right, it'll be A epsilon 0 divided by D, right? Because what you can do is you can take this here, you can take this here, right? Isn't that true? So just take VAB down, take this up, and so it's A epsilon 0 divided by D. So this is what we were looking for. Notice capacitance of the capacitor does not depend upon Q or V, it depends upon the area of cross section and the distance between the plates, right? And this is what you would have expected, because this capacitor has a fixed capacitance. You know, if you have fixed the distance between the plates and if you have fixed the area of these plates, which is fixed, you know, just because you have a higher battery sending out, you know, dumping more charges on this, it's not changing the capacitance of this, because the ratio Q over V is going to be fixed. More powerful is the battery, more will be the Q, such that Q over V is always A epsilon 0 over D. Is that making sense? Any questions? Okay, all the capacitors that you'll see ever will not all be parallel plate capacitors. Oftentimes people use spherical capacitors or cylindrical capacitors. So let's try to figure out what would be the capacitance of, say, a spherical capacitor. So let's try to figure it out. It's not hard at all. And let's say that we have a spherical capacitor like this, which has two concentric metal spheres, and let's say one of them has positive charge on it, uniformly distributed. Of course, if it's a conductor, since it's a conductor, charges will uniformly distribute themselves anyway, right, on the surface. And this is another one which has equal amount of negative charge. So this is minus Q, this is plus Q. Let's say that the radius of the inner conductor is r of A. Let's say the radius of the outer conductor is r of B. Does this configuration fit our definition of what a capacitor is? It does, right? Because you have two conductors, one is this one is this one, they are both spherical and they are separated by an insulator. Let's say again that we have vacuum. We don't have any insulator either, we just have nothing, vacuum. Later on I'll tell you how things will change when you start putting some insulator in between. Okay, so here is the situation. So how am I going to find what is the capacitance of this capacitor? First of all, even before you do anything, can you tell me that capacitance depends upon which things here? Go ahead. Sorry?
It's the area and the radius.
Right, it will only depend upon the geometrical properties again, right? It shouldn't depend upon Q, how much is Q, or there must be some VAB here between the two plates, but it shouldn't depend upon VAB, because C should depend upon the ratio of Q over VAB such that it's independent of both Q and VAB, it's just a constant for this given capacitor. Does that make sense? So if you increase the voltage, the battery voltage that is being used to charge these plates, then Q will increase correspondingly such that Q over V is constant. So let's try to figure it out. So how will we figure out this? Again, let's go back to what you have already learned in the last chapter. Does anybody remember what is the potential? Because one thing we have to do, we know that C will be Q divided by VAB. Q we already know is given for each plate. We need to know VAB. Is it easy to figure out what is VAB? If you flip your notes from yesterday, you would. Because what was the, do you remember we found the potential due to a uniform sphere of charge yesterday, day before? What was it? First of all, we said that the potential everywhere, suppose let's find the potential due to this charge. Potential due to this charge inside everywhere will be constant. Do you remember? Because the electric field everywhere is 0. And do you remember the fact that the electric field due to these charges here everywhere is 0? 0 electric field means equal potential everywhere. Remember we said that when the charges are uniformly distributed on a conductor, on a spherical conductor, the electric field everywhere inside is 0. If the electric field everywhere inside is 0, there is no change in potential. You can see change in potential is related to electric field. So the potential everywhere is constant and it is equal to whatever is the potential right at the surface, right? Okay, what about the potential anywhere here between the two plates? Because that's the region that is really of interest to us. When we talk about capacitor, we are interested, excuse me, sorry, between this positive and negative plate. Sorry, that's the region that is of interest, the region between the two plates of a capacitor. So who wants to tell me from last lecture what was the potential? The question is, if you have some charges uniformly distributed on a sphere, what is the potential at a distance r away due to this sphere? We had done this last time. Go ahead please. Excellent. It was as though the charge that was uniformly distributed on the sphere was just a point charge, right? Do you remember that? Okay, great. So that means the potential here due to this charge will be kq over this q over r, right? What about the potential due to this negative? It'll be whatever that constant potential is, right? Do you see what I'm saying? Due to, if you ask me what is the potential inside at some distance, this is the same as whatever is on the surface everywhere, but the potential is the same because the electric field is 0 everywhere, right? Okay, so using that logic, using this logic, now I want to figure out what is the difference in potential. I want to know what is the difference in potential, say, between this point which is really, really close to this positive plate and a point which is infinitesimally close to the negative plate. You're almost touching the negative, but you're right there. All right, so tell me what would be VAB. First of all, you already told me what is VA. Somebody already told me VA will be, because VAB is really nothing but VA minus VB. It's the potential at this point A, let's call it sphere A, and this is sphere B. So basically VAB is the potential right here minus the potential right here. So what would be the potential right here, folks? Go ahead. It'll be K Q over RA, very good, and VB will be? KQ over RB, right? Yeah. So this is what the potential difference is. Okay, what is it? So let's try to solve it. It looks a little complicated, but it's really not. So what we have is VAB is equal to KQ, and we have RA minus RB, and so what would be C then? Who wants to tell me what is C? See, C is equal to Q divided by VAB. What will it be, folks? Go ahead. Very good. It's 1 over K times 1 over RA minus 1 over RB. This is your answer. This is the capacitance of a spherical capacitor. And notice K, what is K here? Does everybody remember K is really nothing but, another way to write this would be 4 pi epsilon 0 divided by 1 over RA minus 1 over RB. Because K is 1 over 4 pi epsilon 0, right? Do you remember that? So this is the capacitance of a spherical capacitor, and you can see, just like somebody just pointed out, it should depend only on the geometrical properties of the capacitor, and it does depend only on RA and RB. Is there any question about this? Okay, while we are at it, let's find out the capacitance of a cylindrical capacitor, because you could have a capacitor in which there are two cylinders, concentric, two metal cylinders, and then there's some insulator or vacuum between them. Okay, so let's try to figure out. Any questions about this, folks? Okay, so then let's move on to figuring out capacitance of a cylindrical capacitor. This is still true, C is equal to Q over VAB. This is still true, VAB is equal to VA minus VB. Now we need to figure out what is this thing for a cylindrical capacitor. So again, we are always going to make this, so this is one metal cylinder, and we are going to always make this approximation that these cylinders are infinitely long. So we can use the results for infinite cylinder of charge, and then concentric with it, we have another cylinder here, and let's put, say for example, positive charge on this cylinder, and let's put negative charge on the outer cylinder, and let's say we have vacuum between the two cylinders. Is that making sense, folks? So this is one metal cylinder, little one. Let's say the radius of this is r of A. This is another metal cylinder, and let's say radius of this is r of B. Okay, and we have to find out how much is the potential difference VAB between this and this. So let's call it cylinder A, and this is cylinder B, and we are trying to find what is VAB between these two surfaces, between the inner cylinder and the outer cylinder surface, right? Do you remember this is also something that we did last time? Yeah, this is basically like a line of charge, right? And do you remember we found that the electric field due to a line of charge was, so last time we had figured out that due to a line of charge, electric field had a magnitude lambda divided by 2 pi epsilon 0 r, right? And we used this, and we made use of the fact that potential difference is related to the integral of electric field. Do you remember that we put lambda divided by 2 pi epsilon 0 r, and we said integral of 1 over r or 1 over x is log? Do you remember we said that it's natural log? And so we found that the potential VAB in that case gave us so VAB here will be integral of E dot dl, and when you do this integral, it turns out to be lambda divided by 2 pi epsilon 0 log of RA over RB. Does that make sense how we got this? Because we are trying to find potential difference, not electric field. So you have to put the electric field here, and it will become dr divided by r, which is natural log of r, and when you put the upper and lower limits, this is what you'll get, right? Okay, so who wants to tell me, somebody from last row? In this case, one problem that we have is that lambda needs to be written in terms of, say, q, the charges on these things. So we can do that. We can actually say, oh well, let's say, do you remember lambda was defined like this? Charge per unit length. So in other words, you can say that VAB is equal to charge per unit length times 2 pi epsilon 0 log of RA over RB. Is that making sense? So looking at this, can anybody tell me what is C now? What is the capacitance of this cylindrical capacitor with radii RA and RB? Remember, capacitance will be charge per unit voltage. Go ahead folks, help me out. Huh? Q divided by V, right? Can I take this up? Yeah, so it will be L 2 pi epsilon 0 divided by log RA over RB. Isn't this the answer? Any questions about this? Again, I want you to note that this thing only depends upon the geometrical properties of the capacitor and not on Q or V, right? Because as V increases, Q will increase such that Q over V stays this constant. Is that making sense folks? Any questions about how to find the capacitance of a parallel plate capacitor, spherical capacitor or cylindrical capacitor? Clear? Okay, now in most electronic circuits we already know if you look at any electronic chip, it doesn't have one capacitor. It has actually billions of capacitors. Many of those capacitors are connected to each other in different ways. We are going to talk first about two special ways of connecting these capacitors together. They are called capacitors connected to each other in series and capacitors connected to each other in parallel. And what we are going to try to do here is figure out how to replace those capacitors with just one single capacitor, which we'll call an equivalent capacitor. So let's try to now figure out capacitors in series and parallel. So first let's talk about capacitors in series. And I already told you that I am going to denote capacitors with two vertical lines which are equal in length, okay. So when I say capacitors are in series, I mean capacitors are like this. Let's say that the capacitance of this capacitor is C1 and the capacitance of this capacitor is C2. And now I'm going to connect these to a battery. This is a battery which has a potential difference VAB. Maybe this is 3-volt battery or 6-volt battery or let's say 9-volt battery. So okay, initially the circuit is open. As soon as I close the switch, what do you think will happen? Any thoughts? What do you think will happen if I had two capacitors connected like this, which I call series arrangement? What do you think will happen? Again, wouldn't you say that just like the way we talked about at the beginning of the class, wouldn't there be a potential difference as soon as this thing is shut, electrons will start moving from the negative towards the positive? But the problem is, again, this is an insulator between the two plates of a capacitor and this is an insulator also. So it's true, electrons start to move like this, and they'll go this way, but then they cannot cross this. So what do you expect? What are you thinking will happen? Somebody who hasn't said, tell me what is clear that will definitely happen. Go ahead please. Charge. So first of all, here what kind of charges will accumulate on this plate? Very good. These will be negative charges, and where are these negative charges coming from? They must have they must have left behind positive charges, right? So this will develop equal amount of positive charge. What about these plates? You are going to say something. And why would that happen? Very good, because of induction. So the thing is, you can see that it's not that these electrons will jump through vacuum and go to this side, but rather these negatives will induce positive charges here. In other words, electrons on this side in this metal would hate these positive charges, they'll run away and they'll actually accumulate here, and they've left behind positive charges. So by induction you get a separation of charge even on this conductor here. Does that make sense, that here you have a conductor, this wire is a conductor which is connected to these two plates? Would you say that the charge here on these plates is the same as the charge here on these plates? Yes, and that is an important thing to remember about this arrangement, which is called series arrangement. In series arrangement, all capacitors will always have the same exact charge on the plates. Okay? So if this is plus Q, this is minus Q. If this is plus Q, this is minus Q. So the thing is, charges are same on capacitors in series. Okay. Now what is, on the other hand, the potential difference is not going to be the same. You know, depending upon the capacitances here, it's possible that the potential difference across this, you know, might be V1 between the two plates, and here between these two plates it could be V2. When the battery current stops, you know, when these electrons, do you see again that as the electrons are moving, this is getting more negatively charged, this electric field is trying to push the electrons back, and there will be a point at which the electrons won't accelerate anymore in these wires, right, and the current will stop. Do you see that? When do you think that will happen? What should be the relationship between VAB and the potential difference across these two plates and V2, which is the potential difference between these two plates? Go ahead.
It should equal the sum of V1 and V2.
Very good. So the current will stop when VAB becomes equal to V1 plus V2. But V1 and V2 don't have to be the same, it will depend upon what is C1 and C2. But is everybody appreciating, since these capacitors are in series, they must have the same charge. That's an important thing to remember. Okay, now what is our goal here? What I want to do is I want to replace these two capacitors with one single capacitor. Okay, so I want to replace them an equivalent capacitor and what do I mean by an equivalent capacitor? This capacitor has some C equivalent, the equivalent capacitance, which I call C equivalent, such that if I connect it to the same exact battery, this VAB is exactly the same as in this case where we had two capacitors. I get exactly the same charge across the plates of this. So this should have the same exact Q, sorry. You know, for example, if your fan is not working, okay, it's really hot, and you just say, oh my gosh, you know, how do I fix it? And you seem to have some, and it turns out fans have capacitances, and oftentimes those things, you know, stop working. You need to replace the capacitance in your fan. And suppose you don't have one capacitance that you need. This might be, let's say, 3 farads. If you had some other farads, if you knew how to combine them together to make a capacitor that will do the same job, wouldn't you be happy? Because then you can use the ones that you have, put them together to create the one that your fan needs, and hey, you're getting this cool breeze and you're saying, ah, great, I'm able to do something good for myself today. So the thing is, it's a good idea to know how to combine these capacitances to produce the same net effect, you know, for the same exact battery voltage. All right, so how will I do that? So in order to do this, it's not very complicated, so let's figure it out. So the question is, what is C equivalent? This is what we are trying to, in terms of C1 and C2. This is the question we are trying to answer. Okay, first of all, can you tell me what should be the relationship between the potential difference V1 across this capacitor, this is V1 here, the capacitance C1 of this capacitor and the charge Q? Who wants to tell me? We know because C1 should be equal to Q divided by V1. Isn't this true by definition? Capacitance is charge per unit voltage. Here the charge is Q, voltage is V1 across the plates, right? Okay, similarly, what about C2? Can I say C2 is equal to the same exact charge Q because they are in series, but a different voltage V2? Are these looking good? On the other hand, for C equivalent, what do we have? For C equivalent, do you see that V should be equal to VAB? For this one, there's only one. So is everybody seeing this, that C equivalent should be equal to the same Q divided by V, the total V? And hey, we can make use of this. We know that VAB is equal to V1 plus V2. So let's try to see here from here, bless you, we see that V1 is equal to Q divided by C1. Similarly, from here I see V2 is equal to Q divided by C2, and here I see VAB is equal to Q divided by C equivalent. But I know this, I know that VAB should be equal to V1 plus V2. In other words, the total voltage across the battery should add up to the voltage of across this capacitor plus the voltage across this capacitor. And that means, let's plug things in. That means Q over C equivalent, which is VAB, should be equal to Q over C1, which is V1, plus Q over C2, which is V2. All the Q's get cancelled, divide throughout by Q, and what we end up with is this. We end up with 1 over C equivalent is equal to 1 over C1 plus 1 over C2. This is equivalent capacitance of capacitors in series. Another way to say it is 1 over C equivalent is 1 over C1 plus 1 over C2. This is for capacitors in series. Okay, try to do two problems right now. I want you to find C equivalent when C1 is 1 farad and C2 is 1 farad, and I want you to find C equivalent when C1 is 1 farad and C2 is 1,000,000 farad. Everybody should be taking the time to do this. You have 2 minutes. You don't even need 2 minutes. So just plug the things here. For this case, C1 and C2 are both 1 farad. What is C equivalent? Here it's 1 farad, here it's 10 power 6 farad. What is C equivalent? This time I'm going to pick one person and ask them to tell me what the answer should be. Alright, somebody from the last row, answer to the first one. 2 capacitors, each of them is 1 farad. This is 1 farad here, this is 1 farad here. What can I replace it with? That will be equivalent. Anybody? Go ahead please. Sorry? Half, right? Because the thing is, if I put this equal to, so this is 1 divided by 1 plus 1 divided by 1, which is 1 over 1 plus 1, which is a half. think you meant half. So okay, so half farad, right? So you can see that if you have each of these be 1 farad and 1 farad, C equivalent should be half a farad. Is that making sense to everybody, folks? Any questions about this? What about for the second case? Anybody has the answer for the second case? Go ahead, please.
1 farad.
Very close to 1 farad, so you're right. So for the second case, I told you it's 1 farad. This one was 10 to the power 6 farad, and the question is, what should this be, right? We can use the same exact result over there, and we can say C equivalent is 1 divided by 1 over C1 plus 1 over C2, which is 1 over 1 plus 1 over 10 to the power 6, right? And notice that this, if I try to find its LCM, this is 10 power 6 plus 1 divided by 10 to the power 6, which is really 10 to the power 6 divided by 10 power 6 plus 1 farad, which is pretty close to 1 farad actually. So what he said is absolutely correct. If one of them is 10 to the power 6 farad, one of them is 1 farad, they are both connected to each other in series, you can replace them with one equivalent capacitor, which is really 10 power 6 divided by 10 power 6 plus 1 farad, which is roughly equal to 1 farad. 1 farad capacitor might do. One moral that you get from here already is that the equivalent capacitor for two capacitances in series is always smaller than the smallest capacitor. Do you see in this case, for example, each of them was 1 and their equivalent is half. Isn't half less than 1 and 1, both of them? In this case we had 1 and we had 10 power 6, and this number 10 power 6 divided by 10 power 6 plus 1 is smaller than both of them. It's smaller than 1 and it's smaller than 10 power 6. Does that make sense, folks? So the way this result works out, the equivalent capacitor of two capacitances in series is always going to be smaller than each of them. Look at this case here. Here I have two capacitors in series, and it turns out both of them are equal. Both of them are 0.068 farad, 0.068 farad. Let's try and see what is their, what's the voltage across each of them. Wait. Okay, so do you see that the potential difference across this capacitor is 3.9 volts? The potential difference across this capacitor is 4.3 volts, so they're not quite equal even though it says equal. They're a little bit different, and that's why the voltage is different across them. But do you see that if I add this is like V1. Okay, this one is showing you V2. All right, if you add these two, that should be equal to the battery voltage, 9 volts, right? In this case it's not 9 volts, it's the sum of these two, and do you see this is pretty close to the sum, 8.2. So the fact that this one seems to be a little bit lower voltage than that one, what does it say? Which one is a little bit higher capacitance? Tell me, because remember, C1 will be equal to Q divided by V1, C2 will be equal to Q divided by V2, right? So from here you can tell that V1 is equal to Q divided by C1. Q is the same, right? If they are in series, then Q must be the same. So which one has a larger capacitance? The one that is showing a smaller voltage, right? This one must have a slightly larger capacitance than this one, which is showing 4.3 volts. Is that making sense, folks? Any questions about this? Anybody? Okay, then let's now talk about another way of putting these capacitors together, and that is called the parallel way of adding these capacitors in a circuit. So what is the parallel way of putting these capacitors together? Okay, so suppose you have one capacitor with capacitance C1 and you have another capacitor with capacitance C2, and they are connected to the battery like this. Here is a battery which has a voltage VAB. Maybe this is a 9-volt battery, maybe it is a 3-volt battery. Let's make it a 9-volt, it doesn't really matter. This kind of an arrangement is called capacitors in parallel. In this case, it turns out that what is the same across the two capacitors is the potential difference or voltage. So the potential difference or voltage is the same across each capacitor. So what I mean is that in this case the potential difference across C2 will be VAB when the current stops, and the potential difference across C1 will also be VAB when the current stops. Okay, notice something very interesting. By the way, in this course what you have to understand is that these wires, we are not going to worry about capacitance of the wire or resistance of the wire, etc., when we talk about, or inductance of the wire, because we are going to use these new words every day now. You know, we'll talk about resistance and inductance, and today we are talking about capacitance. These are three important parts of the circuit. The wires that we have, we are not going to worry about their inductance, capacitance or resistance. Okay, so in this circuit the only capacitances are due to this capacitor C1 and this capacitor that has capacitance C2. Okay, so if I change this circuit and made this wire longer like this, have I changed anything? No, I haven't changed anything. You know, even if this wire is looking like this, it doesn't matter. You know, we are not worrying about the capacitance or anything of this wire. So the thing is, the only thing that we need to worry about is how are they connected to each other. This junction is something that you should worry about. So long as the junctions are exactly in the same place, the length of this wire, you know, how long these wires is not important. Does that make sense? So is this thing the same as this? Let me ask you this question. Is this thing exactly the same as this? The answer is yes, because the important thing is, if you notice, you know, this thing is again just a wire. You know, it's like this. This thing is nothing but just a wire like this. You notice that basically there is a junction at which these two capacitors meet. There's another junction where these two meet, and they also meet the battery at that junction. They also meet the battery at the junction. And then I know that all of these capacitances, both these capacitances are in parallel with each other, and they are also in parallel with the battery itself. By the way, is this thing clear to everybody why these are all the same? How long of a wire you have or how the wire is meandering is not important. Just look at the junctions. That's what's important. Now what do we want to do? Our goal again is to replace these capacitances in parallel with one capacitance, which we are going to call equivalent capacitor, such that by the way, this time will the amount of charge on these things be necessarily the same? The answer is no. Why? Because think about what's going to happen. Suppose you had a switch here. Okay, as soon as you close the switch, what will happen is that these electrons here will start to move, right? Is everybody seeing electrons will want to go from the negative towards the positives? Here is the problem. So these electrons are wanting to move in this direction. They go like this. At this point they have to decide, do they want to go this way or they want to go this way? And it turns out some of them will go this way, some of them will go this way, but what fraction go this way and accumulate here, versus what fraction go here and accumulate there depends upon the capacitance of those two capacitors with respect to each other. Do you see what I'm saying? And hence, and of course on this side you will have equal amount of positive charges, but the point is that Q1 and Q2 will not be the same this time. What you want in the equivalent capacitor is some charge Q which is equal to Q1 plus Q2. Okay, if you use the same exact battery with potential difference VAB. Is the question clear to everybody what we are trying to do? We are trying to replace two different capacitors which are in series, which are in parallel to each other and to the battery, and the potential difference here is V, the potential VAB, the potential difference here is VAB, which is the same as the battery voltage, because all three are in parallel to each other. We want to replace them with one capacitor that has the total charge Q1 plus Q2, and when I connect it to the same exact battery. This is my goal. Is the goal clear? Okay, how can we do it? It's again, we should be able to do it because tell me what should be the relationship. Who wants to tell me the relationship between Q1, C1, and if we are saying this has to be VAB, this has to be VAB. Tell me, should C1 be equal to Q1 divided by VAB? Similarly, shouldn't C2 be equal to Q2 divided by VAB? And C equivalent should be equal to Q1 plus Q2, which is the total charge, divided by VAB. So look, from here you are getting VAB is equal to C1 over Q1. From here you are getting VAB is equal to C2 over Q2, and from here you are getting VAB is equal to Q1 plus Q2 divided by C equivalent. Right? So what can we do? Any thoughts on what we can do? Or another way to say this is, let's not even bother with this. We can just say C equivalent here. Do you see C equivalent here is equal to Q1 over VAB, this, plus Q2 over VAB. So in fact the easiest thing is just look at this. What is Q1 over VAB? Is that C1? Yeah. So this is just nothing but C1, and this is nothing but C2. So what we find is that C equivalent is equal to C1 plus C2. This is what we wanted to find. So in this case, if suppose this is 1 farad and this is 1 farad also, what would be the equivalent? What would be the C equivalent, folks? Should it be 2 farads? Yeah, so this is for capacitors in parallel. Okay, what happens if one of them is, if C1 is 1 farad and C2 is 1,000,000 farad? C equivalent, if they are in parallel, would be 10 power 6 plus 1 farad, right? Do you see that? So when the capacitors are in parallel, the equivalent capacitance is just the algebraic sum of the individual capacitances. Please. Which equations? Here? Oh, yeah, you're right. I mean, this should be, thank you very much. Thanks a lot. Q2 over C2. Actually, we didn't make use of these relations, but you're absolutely 100% correct. This is absolutely correct. So is everybody seeing that C equivalent in this case is just C1 plus C2? So in this case, the equivalent capacitance will always be greater than the individual capacitances because it's the algebraic sum. Look at this here. These two capacitances are in parallel. Okay, they turn out to be pretty close in voltage. So let's see what happens when you can see that when the current stops, each of them has 8 volts across them, and that is equal to the battery voltage also. Does that make sense? So these two capacitors are connected to each other in parallel. By the way, these two happen to have the same capacitances. What happens if their capacitances were different? Would they still have the same voltage across them since they are in parallel? Yes, that's what I'm trying to say. I'm trying to say to you that even if this one was 1 farad and say this one was 10 to the power 6 farad, doesn't matter. Each of them will still have the same potential difference across them. That's what makes them parallel, in parallel with each other. When the potential difference across two capacitors is exactly the same, you say that they are in parallel. You see, the important thing is how they are connected. So in this case, they will always have both junctions be exactly the same. So both of these capacitors should be meeting at the end at 2 junctions, and there shouldn't be anything else in between. So look, this one is joined at this junction, this one is joined at this junction, this capacitor is joined at the other end with this junction, and here at the other junction. There's nothing else in between here. That's why these things are in parallel. Is that making sense? Okay, now what about those cases where the capacitors are partly in series and partly in parallel? So let's try to do those cases. So capacitors partly in series and partly in parallel. By the way, even before I do that, let's try to do a little bit more problem. So suppose we had been given that this VAB was 9 volts. Suppose we had been given that VAB was 9 volts. Can we figure out, and suppose we have been given that C1 is 1 farad and C2 is 10 to the power 6 farad. Can we figure out Q1 and Q2? So the question is here, tell me what is Q, what is Q1, what is Q2? Because I think you'll see some homework questions like this. Please.
We can't see the question.
Oh, the question is here. You can see these ones?
No, I can't see the behind the
Behind this thing? Okay. All I said was that, let's say that we had a battery with voltage VAB, which was 9 volts. Okay. Let's say that we were given that C1 was equal to 1 farad, C2 was equal to 10 to the power 6 farad. These two were parallel to each other. And to battery, and parallel to the battery. And the question was asking, what is C equivalent, what is Q1, what is Q2, and what is Q on the equivalent capacitor. This is what I wrote. Thanks. So tell me, how would we do it? Have we found C equivalent already? Since these are in parallel, C equivalent should just be 1 plus 10 to the power 6 farad, right? Okay, who wants to tell me what would be the next thing to tackle? Q total. Q total will be the next thing that would be easy to tackle, because we know that Q total should be equal to C equivalent times VAB. Isn't that true? So we know that this would be the easiest thing to tackle, because Q total is equal to, from there you can see it's C equivalent times VAB. And we know C equivalent, we just now found it's this, times VAB. So Q will be equal to 9 volts times 10 power 6 plus 1, and so the answer will be this many coulombs. Is that making sense? Okay, what about the other thing? Can we figure out what is Q1? How do I find Q1? Can I say Q1 is equal to VAB times C1? Yeah, and Q2 is equal to VAB times C2. So Q1 will be C1 times VAB, which is 1 farad times 9 volts, this many coulombs, and Q2 will be C2 times VAB, which is 10 power 6 farads times 9 volts, which means 9 times 10 power 6 coulomb. Boy, that is some kind of charge. That's a huge charge, you know. So the numbers that we have chosen are a little bit crazy numbers. We should have chosen smaller numbers because even 10 power minus 6 coulomb is pretty big charge. So these are turning out to be crazy charges. Anyway, is the idea clear to everybody? All right, so let's then move on to thinking about cases where you might have some capacitors in series with each other and some in parallel. In this case, you know what is the trickiest? And you have some homework questions like this. The trickiest part is not to, you know, get really tempted to do all of them at the same time. I assure you, if you go slowly, you'll not make mistake, because all the people who make mistakes in those problems are those who are saying, oh, I can handle them all at the same time. So let me tell you what I mean by that. So suppose you had a question that said, here is the thing, you have a circuit like this, you have a capacitor C1, which might be 1 farad, you have a capacitor C2, which is maybe 2 farad, you have another capacitor here, which is C3, which is also 2 farad, and you have another capacitor here, C4, which is 3 farad, and you have another capacitor here, C5, which is 3 farad. And the question is asking you, okay, so here is some battery, plus minus, this is your VAB. The question is asking you, what is C equivalent of the circuit? Okay. I have seen that people have this temptation to jump and try to do all of this at the same time, and that's when you go wrong. So what should be the right way to do it? Go slow. Deal with the ones that you're 100% sure about. You know for sure you'll be able to bet that these two are definitely in series or in parallel. Only do those first and try to compress them into an equivalent capacitor. Then move to the next one. So here, does anybody want to tell me that they're 100% sure two capacitors are definitely either in series or parallel? Go ahead.
C4 and C5.
Okay, she is saying that C4 and C5 are definitely in series? How many people agree with her that C4 and C5 are definitely in series? She's absolutely right. C4 and C5 are definitely in series. Look, there is no junction between them. Do you see that this is just one line? By the way, if I had moved C4 just from there instead of there, if it was here, would it have mattered? No, it wouldn't have mattered. It's just a wire. There's no junction or anything, right? So the same charges will accumulate on C4 and C5. So I know that C4 and C5 are definitely in series, right? So can I combine them into one? Yes. So I can combine these two and replace them with just one. And what would be the equivalent? You know, let's call it the equivalent of 4 and 5. Let's give it a name, C45. Out of lack of creativity, let's just give it that name. And that would be what? 1 over 3 plus 1 over 3. How much is this then? This turns out to be 3 over 2, right? Farad. Okay, good. Now, who wants to tell me which two things they are sure are either in series or parallel? Go ahead. Okay, so you are saying that this equivalent capacitor is definitely in parallel with this, and those two are also in parallel with this? Actually, he's right. So the thing is, if you look at, but let's do it one at a time. So if you look at these two, if you look at this junction, do you see there's a junction here? Do you see that there is nothing between this one and this one except those two wires are meeting at that junction? Similarly, here, this end of this capacitor is meeting this end. So there's nothing, so these two look like they're in parallel, right? And similarly, there's nothing over here either. You know, this thing is in parallel with that also. So if you like, do you want to do all three at the same time? Is everybody seeing that this one, this C2 is in parallel with C3 also? We can do all three at the same time. Because if the equivalent capacitance of two parallel capacitors is, you know, just C1 plus C2, if there were three in parallel, it will just be C1 plus C2 plus C3, right? If I put another one in parallel like this over here, see, to this circuit, if I put another one like this, if this was C3, go ahead please.
At the same time, couldn't you recognize C1 and C2 in series and then?
Okay, that's a very good point, and the answer to that, you know, that's a common thing that you can do wrong, incorrectly. That's a very good point that you brought out. Thank you so much. C1 and C2 are neither in series nor in parallel. Right now, C1 and C2 are neither in series. First of all, why are they not in series? Because if you think about, say for example, if they were in series, we said they would collect same charge, right? Think about it. This battery, as soon as you, let's say we had a switch, as soon as we close the switch, electrons will start flowing like this, right? Do you see that the electrons, as they flow, there will be some charges accumulating here, but at this point the electrons have to split. So the charge that is accumulating on this plate is not the same as the charge that will be accumulating there, and so it cannot be in series. Series means no junction. There shouldn't be anything, you know, if I put lots of resistance, capacitances here, these are all in series with each other. But as soon as you see a junction, no, anything after that is not in series. Here there's a junction here. And because of this junction, C1 is not in series with C2. Also, they're not even in parallel. Why are they not in parallel? Why are C1 and C2 not in parallel? Anybody? Because see, one easy way to recognize that they will have the same potential difference across them, that means they are parallel, is to see, are there two ends meeting at a junction and there's nothing else in between. So let's see, this end of this capacitor, this end of this capacitor, hey great, they are meeting at a junction, looks like it might be, but let's look at the other side. Hey, if I look at this thing, oh, there's a problem, they're not meeting at this junction, there's a battery in between. If this battery was not there, if it was just like this, then yes, C1 and C2 would have been in parallel with each other. Do you understand what I'm trying to say? But the fact that there is a battery here, they are not in parallel. On the other hand, okay, I want to stop here, but I hope that you guys got the idea that these three capacitors are in series with each other, right? All right, I'll see you guys next time. Have a great day.
Professor Singh is a lecturer in the physics department at the University of Pittsburgh. For more information about Professor Singh and her research, visit her website in the description below.